Here we are back in Unit 1, talking again. This is Part 2 for Topic 1.7. So we've already talked about ways to use statistics, numbers that describe data, to talk about the center, the mean, and the median. And then we talked about other positions like the quartiles. But now we're going to talk about ways that you can measure the spread of data. So let's just jump right to it. So remember, the spread of data is talking about how your data varies. So think of this as a single number that tells you how much the data varies. Like a big number would tell you, wow, the data really varies, versus a small number would tell you, oh, wow, your data is pretty consistent. It doesn't vary a whole lot. So we have three ways to do this. We have the range, the interquartile range, and the standard deviation. All right, so the range is one that I hope everybody's heard before. It's simply the max minus the min. It's the difference between the max minus the min. And think about this. If there's a big difference between your max and min, if your range is big, then you're going to get a big number telling you that your data is really spread out. If your max and your min are pretty close to each other, then you're going to get a small range, and it's going to tell you that your data is pretty consistent and not spread out. But the problem with the range, the one reason why we don't necessarily love the range, even though it sounds so easy, is that it's easily influenced by outliers. So if you have a set of data that looks like this, 2, 4, 4, 5, 6, 6, 7, 83. Well, then it looks like you're going to have this big range. Like, wow, I have a range of 81. That's a pretty big range. But that's actually misleading because you have an outlier. If you take that outlier away, your data is very, very consistent with a very small range of 5. This is something that outliers do, and that's why we don't necessarily like them. So we know the range, we understand the range, it's the max minus min, and if you're asked to find the range, like, don't exclude an outlier. Like, the problem with using the range is sometimes it looks bigger than it really is, but if the definition of the range is max minus min, then you got an outlier, you got to use it to find the range. But it's the reason why we just don't necessarily always use it or like it. The second one is called the interquartile range. I would guess that most of you have never heard this before. This is the IQR, interquartile range. This is the spread of the middle 50% of your data. So remember, the quartiles break your data into quarters. So the median is in the middle. That's the second quartile. Here's your min. Here's your max. The first quartile and the third quartile. It's like breaking a dollar into quarters, right? So again, this breaks your data into these 25% chunks. 25, 25, 25, 25. So the middle 50%, the range of the middle 50% is the IQR. It's literally Q3 minus Q1. It's easy. Now, the reason why we like this number better is it's not influenced by those outliers. So if you do have that big outlier over here, 87 or whatever, all of a sudden it doesn't matter. The interquartile range does not look at the outside 25%. It only looks at that middle 50%. So it's telling you the spread of the middle of your data. We like it. It's a great value. All right. The last one is probably the most important and the one that we're going to actually use the most this entire year, and that is standard deviation. The standard deviation is a great way to measure your data. Now, the standard deviation is a number that tells you a typical distance a value is from the mean. It tells you how far data typically is from the mean. How far data is from the mean. Up, above the mean, down, below the mean. Above the mean or below the mean. How far the data is from the mean. So let me just do some examples until I start looking at more here. If you have a mean of 10 and you have a standard deviation, by the way, the symbol for standard deviation is S, is 2. This means that most data is from 8 to 12. 2 above, 2 below. Most data is from 8 to 12. Not all data, most data. The typical data, the typical value is somewhere between 8 and 12. 2 above, 2 below, right? I mean, I hope I'm making complete sense here. If your mean is 80 and your standard deviation is 20, now you're more spread out. Your data ranges, most of your data goes from 60 to 100. 60 to 100. Most of your data is 60 to 100. Not all of your data is in there, but most of your data spreads from 60 to 100. Standard deviation below, standard deviation above. So again, the standard deviation measures how far your data is from the mean. Now here's the bad part. The formula to find standard deviation is very complicated. So the first thing you have to do is you have to find how far each individual value is from the mean. So this little xi is an individual value. So how far is each individual value from the mean? Then you square that value. Then you add, remember this is that crazy symbol for add. You add all of those values together. And then you multiply by 1 divided by n minus 1. Don't ask why. Then you take the square root. So let me just get you the good news right now. You're never, ever, for me, going to be asked to calculate the standard deviation by hand. Your calculator will calculate the standard deviation with this crazy formula almost instantly for you so that you don't have to waste any time with it. What you need to waste your time dealing with is knowing how to interpret it. Knowing that the standard deviation is where most data falls from the mean. Again, mean 10, standard deviation 2, most data 8 to 12. 2 down, 2 up. Again, that's how they go together. So these numbers have to always be paired. If you don't know the mean, but you do know the standard deviation, then you don't know where you're from. Like if I knew the standard deviation was 5, okay, is that 5 up and 5 down from 30? Or 5 up and 5 down from 2,000? I don't. So you need to know the mean. So this is like peanut butter and jelly. The mean and standard deviation always go together. So how do you find the variability in a data set? Do we do it by hand? Well, we could, but that's not cool. It's going to take a lot of work. Yeah, we use the calculator. So let's look at these 13 females and their commute times one more time. And remember, I'll go through the process nice and slow again. Stat, edit, put the data into your calculator. Doesn't matter the list. Stat, slide over to calculate. One variable stats. Make sure you tell the calculator which lists you used. I used list 2. Leave the frequency list blank, hit calculate, and there's the mean, and S is right down below it. It says SX. That just means the standard deviation of your data. Don't worry about the X. The S is there. So don't worry about these other numbers. We're not going to talk about them right now, but again, S is the standard deviation, 11.129. That's huge, 11.129. So let's come back to our data. So the mean was 20.769. 20.769, and the standard deviation was 11 and I already forget what it was, 11.129. So remember, this means that most data is going to be centered around the mean. So here's the mean. Most data is going to be 1 standard deviation above, so that's adding 11.129 to 1 standard deviation below. Okay, so let's actually go and do that. So 20.769. Let's subtract 11.129. Let's do the same thing again. This time adding 20.769 plus 11.129. So this tells me that most data, not all, most data ranges from about 9 to about 32. And you can do a little bit around, about, whatever. You can round a little bit, not a big deal, but just generally speaking, 10 to 32 is where most data falls. Now let's go back and see if that's true. 10 falls about right here. 32 falls about right here. Hey, what do you know? A big chunk of my data, not all, almost all, of my data falls within that 1 standard deviation of the mean. All right, what about IQR and range? Well, remember when you do that one variable stats and you type in your list and hit enter, remember you could scroll down and you could get the min and the max. So the min and the max allow you to find the range. So 45 minus 5 is a range of 40. That's easy. And then again, to find the IQR, the interquartile range, you subtract the quartiles. So I would do 26.5, that's Q3, minus 13. So 26.5 minus 13. Boom, there is my IQR, the interquartile range. I want to make sure I say it right. That's it. Always use that. Pretty cool when we have the data in front of us. All right, now again, we can also compare variability. So if I say, talk to me about how these graphs are different and how they're similar. So one thing I would say that they're similar is they both have, they're both very symmetric. They're symmetric in two different ways, but they're both very symmetric. And when you're nice and symmetric, the mean and the median are both going to fall pretty much smack dab in the middle. So I would think about 35, and again, I don't know for sure. You can never know for sure with the histogram because you don't see the actual data. But I would bet, excuse me, I can't talk. I would bet that 35 is a pretty good approximation for the mean and the median of both sets of data. Because when your mean and your median and symmetric data are going to be right in the middle. All right, but what about the spread? A is going to have a much bigger spread because most data is far from the mean. Look at that. Most data is far from the mean. Very little data is near the mean. Most data is way down here or way up here. In graph B, most data is near the mean. The majority of data is near the mean. So B is going to have a standard deviation much less than A. Because remember, standard deviation measures how far most data is from the mean. So in graph A, most data, typically data is far from the mean. Typically data is really low or really high, far from the mean. That's going to produce a larger standard deviation. Whereas when you're symmetric with all the data in the middle, like a mound shaped, that's when you're going to have a smaller standard deviation because most of your data is near the mean. Makes sense, hopefully. Okay, pretty cool. All right, what about this? So I already mentioned earlier that the mean and standard deviation are best friends, peanut butter and jelly. The mean and standard deviation will always go together in the same breath. If you're going to talk about one, you better talk about the other because the standard deviation measures how far data is from the mean. I haven't said that enough in this video, right? So we love always mentioning them together. So if you're going to say that that data has a mean, you better tell me the data is standard deviation. Now, we love to use the mean and standard deviation when we are symmetric. Symmetric with no major outliers, that is when the mean and the standard deviation are our best friends. The IQR and the median always go together. Let's talk about why. The median is the middle value, 50% above, 50% below. No matter what, it's the dead center of our data. The IQR measures the spread around the median. The IQR measures the spread from Q3 to Q1, which of course includes the median. So the IQR measures the middle 50%. The median is in the middle 50%. So that is why the median and the IQR are best friends. They always go together. Now, we prefer to use them when there is data that is skewed left or skewed right. Okay? Now, again, I will just say this, and some statisticians might argue with me, but the mean and standard deviation are top-notch. They are the much preferred values for talking about center and variability. But the problem is when you are skewed to the right, for example, the mean and the standard deviation can get skewed as well. They can get misconstrued. Because remember, when there are some really, really big values, even if there's only a couple of them, when they do exist, they're going to pull the mean towards them. That's going to take the mean further away from the majority of the data down here, which is going to make the standard deviation big as well. And we don't like when that happens. So we do not want to use the mean and standard deviation in that scenario. We'd much rather use the IQR and the median in that scenario because the IQR and the median are going to focus on the middle 50% of your data. They're not going to worry about the extreme top or the extreme bottom like the mean and standard deviation would. So we prefer the mean and standard deviation, but we only really use those values when we're nice and symmetric. Good news for the future, a lot of data is nice and symmetric. Not all, but a lot. So that's why we like using it so much. Okay? Let's talk about outliers now. Let's talk about how to find outliers in a data set. Because we no longer want it to be like a question mark, like, oh, maybe it's an outlier, maybe it's not. No, we want it to be for certain now. So we do have two common methods to identify outliers. one of them is like the official way. The other one is a good way of doing it as well. But it really kind of all depends on what you have given to you. What data is in front of you and what is given to you can kind of depend on what method you want to use. So the first method we have is I call it the fence method, but it's using the quartiles. So if what you have given to you in a problem is the quartiles, Q3 and Q1, then this method is going to be top notch. So what we do is we find the fences. We find what's called the upper fence and the lower fence. Now, these are imaginary fences. They're not actual values. They don't exist. But what we're doing is we're establishing, like the extreme. If you're outside of the fence on the upper side, you are extremely big. If you're outside of the fence on the lower, you are extremely low. So to find those fences, it's pretty simple math, actually. We take Q3, we add 1.5 times the IQR. Now remember, the IQR is just Q3 minus Q1, so it's pretty easy to find. So we do 1.5 times the IQR. So Q3 plus 1.5 times the IQR is going to produce a number. Any value in your data bigger than that will be an official outlier. For the lower fence, we take Q1 and we subtract 1.5 times the IQR. Once again, this is going to produce a number, an imaginary number. I mean, not an imaginary number like in pre-calc, please don't think that, but a number that it's not necessarily one of your values. It's like a fence value. And we say, okay, any data in our set that is lower than that lower fence is officially called an outlier. So basically, we have our data, people boop, boop, people boop, boop, people boop, boop, people boop, boop, and we calculate these fences. We calculate a lower fence and we calculate an upper fence. And if there is a value below the lower fence, it's an outlier. If there is a value above the upper fence, it's an outlier. If there's nothing above the upper fence, nothing below the lower fence, guess there's no outliers. But this is a nice, very simple way. And you only need two numbers to do this. You just need Q3 and Q1. That's it. And you can calculate the fences. The second method that's honestly not most common is using the fences series. So like if I want you to officially do it, I'd use the fences. But we could also look at it this way. If we have the mean and standard deviation, like maybe we don't know the quartiles, so we can't find the fences because the fences require the quartiles. Then we're going to do option 2 here. Now remember I mentioned multiple times earlier that most data, not all, most data is within one standard deviation of the mean, meaning most data is one above to one below. So if we have our mean here and we add one standard deviation and we subtract one standard deviation, in that range is very common, very typical, very normal data. If a value is more than 2 standard deviations, that's pretty strange. So here's our mean. If we go up 2 standard deviations or we go down 2 standard deviations, any values outside of that, those values are pretty strange. Those values would be considered pretty weird. If a value is more than 3 standard deviations from the mean, 3 up, 3 down, now that is strange. So if here's the mean and we go up 3 standard deviations and we go down 3 standard deviations, any values outside of that, if there are any, would definitely be considered outliers. Those would be very, very extreme values. Again, go back to the idea that most data is within 1. So to be outside of 2 would be strange. To be outside of 3 would be like, what is going on? Highly, highly, highly unlikely. All right, so let's practice this with an example here. So 117 kids at a Pokemon convention were asked, hey, how many Pokemon cards do you have? And here is what we call summary data. So instead of me giving you all the data, because that'd be kind of pretty boring to look at, I'm going to give you some summary data. So there were 117 kids. The average number of Pokemon cards was 129.4. The median was 50. Don't ever worry about true mean. That's outside the scope of this class. The standard deviation was quite large, which right away tells me that the data varied a lot. And I'm going to convince you of that more in a second. Don't ever worry about SE mean. We'll deal with that at the end of the year. We have our quartiles. The third quartile was 95. The first quartile was 30. So I could very, very quickly calculate the IQR by doing 95 minus 30, and that's 65. So the IQR is 65. That's an important number. We also give the min and the max. Now look at that max. That max is huge. One kid had 3,000 Pokemon cards. So no wonder the standard deviation was so big. So I want you to really kind of notice a couple things here. First, notice how different the mean and the median is. The fact that the mean is significantly higher than the median tells me that I'm skewed right. Skewed right. Because this one kid had 3,000 Pokemon cards. So remember, the median is down here at 50, right? 50% of kids have less than 50 Pokemon cards. 50% of kids have more than 50 Pokemon cards. But when you add in this one extreme kid that had 3,000 Pokemon cards, that's going to make the mean go towards it. So no wonder the mean is so much higher than the median. So even though I didn't have a graph of my data, I could get a feel for what that data looks like based solely on this. Now let's use the fence method real quick here. So the upper fence, which I'll call UF, is going to be Q3, 95, plus 1.5 times the IQR of 65. So let me do that math real quick. 95 plus 1.5 times 65 is 192.5. 192.5. So are there any values in our data bigger than that? Well, one of the drawbacks here is I don't have all the individual data values, but I do know for sure 3,000 is an outlier. 3,000 is definitely bigger than 192.5. Now, could there be a kid that has 1,000 Pokemon cards? It's not a max, but it's still bigger than 192.5. Yes. I don't know for sure though. Maybe, maybe not. So I know there is for sure one upper outlier. One upper outlier at 3,000. Might be more. Don't know for sure. But there's definitely one at 3,000. The lower fence is going to be Q1, 30 minus 1.5 times the IQR. So 30 minus 1.5 times 65 is negative 67.5. Now it's negative. Clearly nobody owns a negative amount of Pokemon cards. The lowest was 0, so there was clearly no values below 0. So there's no lower outliers because nothing in the data is lower than negative 67.5 because the min is 0. All right, so I know for sure there's one outlier at 3,000. Could be more, but without the data, I don't know. But if I did have all the data in front of me, anything greater than 192.5 is an outlier. All right, lastly, let's use the idea of the 3 standard deviations. So the mean is 129.4. If I add or subtract 3 standard deviations, which would be 3 times 323.6, this is where outside of this could be outliers. So 129.4. So adding the 3 standard deviations gives me 1,100.2. I know I'm getting really sloppy here. Sorry about that. Kind of trying to rush, but okay. So if I take the mean and I add 3 standard deviations, I get 1,100.2. If I subtract 3 standard deviations, I get negative 841.4. So anything outside of that, anything more than 3 or less than negative 3, standard deviations is definitely going to be an outlier. So once again, the max of 3,000 is definitely more than 1,100.2. So that max value is definitely outside of that window of 3 standard deviations. That's definitely going to be an outlier. But again, same thing. Without the data, I don't know if there's maybe a couple more, but I do know there's nothing on the lower end, right? On the lower end, the min is 0. The one kid had no Pokemon cards. So why was he at the convention? Well, maybe he was just a friend or a mom or something dropped him off. I don't know. But anyway, my point is definitely not going to be lower than 0. So nothing's going to be below that negative 841.4 mark anyway. And again, these are all more indications as to why I'm skewed right? Because basically we're cut off at 0. Nobody has less than 0, but that one kid does have 3,000. That's why everything's kind of skewed to the right. And again, I could clearly see that too by knowing that the mean is so much higher than the median. I'll say this one more time because it's super important. When the mean and the median are pretty much the same, I mean not identical, but really, really close, that's nice and symmetric data. Obviously, it's not happening here at all. All right, that's it. We'll see part 3 for this. It's a long section, I know. Part 3 coming at you soon.